So this gives us, I've given you now a table which lists lots of standard electrode potentials for various equilibria. So we're going to have a look at them. Notice this one here, the hydrogen is set 0. Some of them are negative. That means that these electrodes are negative with respect to hydrogen. These are positive, which means these are more positive than hydrogen. So there's various different ones. You obviously don't need to learn these, you'll be given them. But let's just have a look at the values. Potassium plus an electron goes to potassium solid. The potential of that is minus 2.93 volts. Now think about your chemical knowledge. Is it going to be easy for me to take a potassium ion and make potassium metal? No, that's going to be tough. Potassium wants to be potassium plus ion, doesn't it? He doesn't want to be. Potassium metal is extremely reactive, doesn't stick around. It's a very so this one is very negative. It's very hard for me to take potassium plus and make potassium metal. Let's look at the other end. I have got fluorine gas plus 2 electrons becoming fluoride ions. Is that going to be easy? Fluorine. Or electronegative?
Yeah. No?
Let's...
Okay. I thought the story was really good.
Yeah, it likes electrons. Yeah, it likes electrons. Yeah. Yeah, that's just... very, very positive. It's 2.87 volts. That equilibria really wants to go. Now, how can you think of that in terms of equilibria? Well, this one is F2. I'll avoid using red.
Don't worry, you've got a lot there now.
F2 plus 2 electrons in equilibrium with 2 F minus. That is a very positive electrode potential. What is that telling you? It's positive. So, which side is it going to be? Remember, this sign tells you how many electrons you've got on the electrode. So if it's positive, is the equilibrium to the left or to the right? It's positive. It's going to be to the right. First of all, that makes sense because it wants to be fluoride ion. But secondly, if it's to the right, it means I've removed electrons from my electrode. Yeah, so my electrode, if we had it, okay, I know it's a bit mad, but let's say I had my fluorine electrode, it means that it's lost electrons. Yeah, it's become positive. Let's go the other way. Let's look at potassium. So this would be bonkers if I couldn't do this. I couldn't have potassium metal in a lump with potassium ions, could I, in water? It would just react straight away. Anyway, it is a very, very negative. K plus an electron in equilibrium with K. That is negative. That means that lots of electrons have built up on here because lots of the ions, they've gone to become the potassium atoms have shifted this side. He's become a potassium ion and he's dumped his electron on the electrode. So I've had a big build-up of charge on my electrode.
So it's whatever the electrode?
Yeah, it's telling me how negative that electrode is. So it's giving you an idea. If it's a negative one, if you were just think, if it's negative, the equilibrium is to the left. If it's positive, it's to the right.
I don't like this.
Oh, that's okay. Well, if it's negative, just think that if it's negative, it's an unfavourable reaction. Potassium plus does not want to become potassium metal. So it's negative, it's not likely to happen.
Why?
Because, well, I've measured this, but chemically you know that potassium metal is extremely reactive, isn't it? If I had a lump of potassium metal, it would shift to give me potassium ions pretty sharpish. Yeah? It would much rather be, if I give potassium the option, potassium would rather be K plus rather than potassium metal. So that's telling me the equilibrium is shifted towards the left-hand side.
Very reactive.
Yeah. It would much rather be that side. Equally, fluorine would much rather be F minus ions than fluorine gas. That's why it's a very positive value. So that shifted that side. So the fluorine one shifted that side, the potassium one is shifted that side.
So it has like a full outer shell.
Yeah, that's right, yeah.